Imagine being part construction worker, part emergency repairman, and part disaster response team member. Now imagine yourself underwater, where you'll be wearing heavy equipment while being subjected to crushing physical and psychological pressure. You might even be in a combat zone, or under the watchful eyes of those who consider you a trespasser, or possibly dinner. Such is the world of the Navy salvage diver. It's a career only for those willing to plunge into dangerous situations, to perform hard and exhausting work, often in rough seas, cold water, and unpredictable circumstances. Candidates undergo their initial training at the Navy Diving and Salvage Training Center in Panama City, Florida.
NDSTC overall is responsible for DoD military dive training. We train from 5 services, including the Coast Guard, Marine Corps, Navy, Army, and Air Force as well. We let them know right up front that we're about to challenge you in a mental aspect, in a physical aspect, and a teamwork aspect.
The 155,000 square foot facility has a large pool that is used for physical training and the development of scuba skills. The tower on the property houses a tank where students can begin to make deeper dives in a controlled environment.
The purpose of this facility is we take our students, we put them in the water, they go down to 45 feet, and the primary thing that they do is work on the rate of descent so they can go down at a proper rate, and even more importantly, they want to come up at a certain travel rate, which is 30 feet per minute, so that they can experience the pressure differences from the surface and what's going to be like in the open ocean, so they come up and they don't get any kind of adverse effects from coming up too fast.
In other tanks, students perform various tasks underwater to test their ability to function in an alien environment while wearing heavy diving gear. They learn to use hand tools, underwater power tools, and welding and cutting equipment.
The cutting tool that we use is the Broco exothermic cutting torch. And it has a magnesium core in it. With the oxygen that's supplied to it, it burns at over 10,000 degrees so that you can cut metal, rock, concrete, whatever could be in the way.
Today's students have the advantage of technologically advanced underwater equipment. The Mark 21 dive helmet is standard issue now. It has a fiberglass shell that is weighted for neutral buoyancy and a large faceplate made of the world's strongest polycarbonate plastic. This is the helmet salvage divers currently wear in almost all situations, down to the Navy's imposed diving limit of 300 feet. The Navy uses remotely operated vehicles for dives that are too deep or too dangerous for divers. These ROVs can also be used to assist divers. U.S. Navy ROVs are housed at Phoenix International in Maryland.
Phoenix International is our deep ocean search and recovery contractor. So they husband our equipment. We call it government-owned contractor operated. So the Navy owns the ROVs and the search systems. They maintain them and then they operate them as we need to call them out.
The ROVs can be as small as a suitcase or as big as an SUV. The Deep Drone is one of the more powerful ROVs, able to work much deeper than divers.
With Deep Drone, we take a 9,200-foot spool of Kevlar jacketed cable where all of the power, sonar, video signals come through, terminate into the maintenance van. In addition to these 2 components, we'll take the maintenance hut and the operator hut where 2 people can operate the vehicle.
The pilot controls the drone's thrusters, along with the lights and video cameras. The co-pilot operates the sonar, and he's also at the manipulator station.
There's 7 function manipulators that closely resemble the human arm. They have 7 functions: the shoulder, the forearm, the wrist. It can rotate for us to be able to put shackles together to tie into lift lines, and each arm can lift 250 pounds each in air.
Each salvage job presents its own set of problems, and when the Navy gets involved, it's up to the supervisor of salvage, based in Washington, D.C., to determine what assets need to be deployed to accomplish the task. In 1996, the search and recovery following the mysterious crash of TWA Flight 800, 8 miles off the coast of Long Island, brought many Navy salvage capabilities together. 226 Navy divers, a variety of ROVs, and the ships necessary to deploy them assisted in what turned out to be the longest and most expensive airline accident investigation in American history.
The Navy was working for the National Transportation Safety Board on this operation, who of course was also working hand in hand with the FBI, because there were many theories initially about what might have brought TWA Flight 800 down, including a terrorist attack, a bombing on the aircraft, or there was also the theory that possibly a Navy vessel had accidentally shot her out of the sky with a surface-to-air missile.
There was a mid-air explosion of the aircraft, which basically took the nose of the aircraft off. That hit the water, and the plane, still under power, went in. And what that did is created a very large debris field.
Most of the wreckage was in about 120 feet of water, within easy reach of divers.
As a Navy diver, I made several dives during the operation. And diving on an aircraft accident is one of the hardest things that we have to do as a Navy diver. You have all this twisted, very thin metal, the wreckage of the fuselage, which is like razor blades. And then on top of that, you have miles and miles and miles of electrical wire that was part of the aircraft. So you're constantly having to watch where you step, where you put your hand. You don't want to get tangled up in all that electrical wire. You don't want to cut open your air hose or your umbilical on some of that razor-sharp, twisted metal. But you still want to move as quickly as possible because you know that your job is so important, not only for the investigation, but more so for the families and friends of the victims. And our first job was trying to recover the victims of this horrible tragedy.
The ROVs, with their lights and cameras, offered valuable assistance to the divers during the victim recovery phase of the operation.
What we did with the MRI-1 vehicle was it was kind of used like a bird dog. We would put it underwater, we would search through the area of wreckage for passengers. And then when we found someone, the vehicle would stay there. The diver would go underwater, follow the electrical umbilical down to the vehicle, and then recover the crash victim.
During airline disaster recovery operations, finding the flight recorders, referred to as the black boxes, is another priority. A small acoustical beacon called a pinger is attached to each of them.
The way these devices work is that there are actually a couple of small electrical contacts on the end, which are shorted out when it's immersed in salt water, and it starts chirping. Those small chirps of sound are what people track or try to locate when one of these devices are underwater.
To find Flight 800's black boxes, divers and ROVs used underwater microphones to home in on the pingers.
I was on board the Grasp, and actually what ended up happening was we had an underwater vehicle in the water, and the lights from the vehicle actually lit up the box. Because even though they're called black boxes, they're actually bright orange.
After the recovery of the black boxes and all 230 victims, divers and ROVs began collecting pieces of the wreckage. Because of the controversy surrounding the crash, the goal was to retrieve as much of the aircraft as possible to help determine the cause.
We used the big ROVs to tie into portions of the aircraft, like the wings or the cockpit section. We'd actually run straps or rigging around those pieces. We'd tie lift lines in from the big salvage ships, pull those pieces onto the ship, and send it back to the beach on barges.
As the salvage teams recovered more and more of the aircraft, they began to eliminate a number of sinister scenarios.
We fortunately had diving with us in our scuba teams were our explosive ordnance disposal experts. These people know what they're looking at and what they're looking for. And there was never anything recovered from the debris field that could possibly have been part of a bomb, a missile, or an explosive device of any sort. So in our minds, we knew that that was not a possibility.
By the end of the salvage mission, 98% of the plane was recovered. In a hangar on Long Island, workers pieced the wreckage back together to help determine the cause of the crash.
The current best conclusion is that there was a spark in a pump in the fuel tank that ignited due to a whole series of factors that caused one of the fuel tanks to explode.
The recovery of Flight 800 called into service a significant portion of the Navy's salvage assets. But it was back when salvage technologies were not as sophisticated that the Navy faced one of its biggest challenges: to resurrect much of the Pacific Fleet after the attack that swept the United States into World War II. During the 9-month-long Flight 800 recovery operation, the divers involved made over 4,300 dives. Deep Sea Salvage will return on Modern Marvels. Navy salvage divers working on the ocean floor couldn't perform the important work that they do without support from above. Deep sea salvage jobs in the open seas require a base of operations of one or more ships or barges, referred to as platforms in the salvage business. The pride of the fleet are 4 Safeguard ARS-50 class rescue and salvage ships.
4 ships are USS Grasp, Grapple, Safeguard, and Salvor. The Grasp and Grapple are both stationed in Little Creek, Virginia, and they primarily operate in the Atlantic and Mediterranean. The Salvor is stationed in Pearl Harbor, Hawaii. We operate in the Pacific from California to Southeast Asia. Safeguard is stationed in Sasebo, Japan, and they operate from Japan all the way to the Indian Ocean.
Each Safeguard-class ship is 255 feet long and weighs in at nearly 3,300 tons. The engine room drives 2 propulsion shafts that combine to produce 4,200 horsepower. Top speed is 14.5 knots. Built in the mid-1980s, each ship's bridge has been modified with up-to-date navigational equipment.
Here on the Grapple, I'm standing in front of the 3-centimeter radar that we use to track all the vessels in their immediate vicinity within 48 miles. And we also use it for extra help on tracking our course. In conjunction with our ECDIS, which is an electronic chart computer, it gives us information from these radars. It gets input from the automatic ship identification system. It gets GPS input, gives me depths, gives me all contours of shoreline, and we back up the ECDIS with our paper charts.
To facilitate salvage operations, each end of the ship is outfitted with a boom. The forward boom has a 7.5-ton capacity, but the heavier lifting is done from the back of the ship.
Above us we have a 40-ton boom with a main hook and an auxiliary hook. The main hook is able to lift 40 tons, the auxiliary hook 5.5 tons. Primarily use that if we're going to lift a piece of salvage equipment up onto the fantail, or if we have large pieces of equipment on the fantail we need to move around, we can use it for that.
The boom is also used to hoist the large hatch in the center of the fantail to gain access to the salvage equipment stored in the cargo hold below. Inside, each ship also houses a machine shop to support on-site operations. Large drums hold 3,000 feet of 2¼ inch thick wire rope for salvaging and towing.
The Safeguard class of rescue and salvage ship was designed to tow a Nimitz-class aircraft carrier at around 5 knots. We have the ability to conduct a lift, and we can use the bow and stern rollers to pick up 300 tons off the bottom of the ocean.
The ships are also outfitted with multiple anchors and 4 enormous orange buoys that are used to securely moor the ship over an underwater job site.
There are 2 on each side. Those are called spring buoys, and we use those at the end of a beach gear leg, which is an anchor, length of chain, and then wires that would come up and attach to the buoy. Once we lay the legs of beach gear, the buoys would remain in place, and then we would attach to those buoys with large mooring lines. And we can adjust the length of those lines to move us around inside the moor. The advantage of a 4-point moor is you can move around a large area to conduct diving operations.
Safeguard-class ships not only fully support the divers assigned to them, but also carry full firefighting gear for the crew and divers. The crews can use fire monitors, which are essentially water cannons that spray seawater at up to 1,000 gallons per minute. The Safeguard-class ships were built to modernize the Navy's salvage fleet, which up until that point was still heavily relying on World War II-era ships. Another vintage asset retired about the same time were the dive suits that looked like something out of a Jules Verne novel. The classic Mark V dive helmet and suit underwent some alterations over the years, but this was basically the gear that divers suited up in from the 1890s to the 1980s.
It's very bulky, it's very safe. It was, believe it or not, it's really good for going inside wrecks, working in there, things like that, because you have the hard hat, you have a nice thick canvas protection over the top of you. But the whole rig's roughly about 194 to 198 pounds. It's a good rig, it's solid for working on the inside. It wasn't for this rig in the Pearl Harbor, we never got the ships up, the ones that we did.
Pearl Harbor. It was here in 1941 that Navy divers donned their Mark V's to do their part in the most massive salvage challenge in U.S. history.
It's a nice morning here at Pearl Harbor in the Hawaiian Islands. People are queued up to go out and see the USS Arizona Memorial. But in 1941, on a Sunday morning, the whole place was in flames. It was chaos. Ships were sinking, people were dying. The Imperial Navy had attacked the U.S. fleet stationed here at Pearl Harbor.
After the attack was over, they found that 21 vessels had been sunk or damaged. 7 of those vessels moored along the edge of Fort Island, the great battleships, the main battle line. The fires did burn out of control, but fortunately, the shipyard and the dry docks were intact. So the mechanics and the facilities were available to raise this fleet.
You can imagine what it was like for divers to work in this environment. The waters of Pearl Harbor were filled with oil. There was debris. There were bodies from the ships that had been thrown overboard.
After the initial rescue and recovery efforts, the salvage crews first dealt with the ships that suffered relatively little damage. Underwater patches to the hulls and pumping operations got several vessels either back into service or able to make it to dry dock for final repairs. Within a few months, several ships returned to active duty. Others required more extensive repairs, but it was the capsized vessels that presented bigger challenges.
The Japanese force that came in from the west made a torpedo attack on one of the ships, the mine layer Oglala. Because of the shallow draft of that vessel, the torpedo actually traveled under the hull, striking the Helena behind it.
Well, the Helena exploded, and the shock waves from the torpedoes burst seams in the Oglala. And she took on water slowly and sank. She just turned sideways and went down. Veterans like to say she died of fright.
The salvage team's unusual challenge was to roll over and refloat the massive old mine layer. The solution involved the use of a pontoon system, originally devised to raise sunken submarines and ships off the bottom.
The idea of the salvage pontoon is to float them to either side of the sunken vessel. You then fill them with water, drop them down, pass cables underneath the vessel that's sunk, and secure these pontoons to either side.
Once these were on the bottom, next to the ship, they would bring hoses along to pump out the water and fill these now with air. This gradual process allows these pontoons to be used as a lifting body to bring that ship up to the surface, so these act as life vests around the ship.
But the Oglala, lying on its side in the harbor, required a new and untested approach to using the pontoons. One was positioned at the bow, 3 on the stern, and 6 on one side of the vessel. Chains were attached to the pontoons along the side, passed under the ship, and secured to the starboard side. Then the pontoons were pumped full of air. As they rose to the surface, the chains rolled the ship back over. The first righting attempt failed because some of the chains broke loose. But 12 days later, on April 23, 1942, the Oglala was successfully pulled upright. Divers could now patch the damaged hull. The water was pumped out of the ship so it could be moved to dry dock And soon, the Oglala was seaworthy again. Today, the USS Missouri, the battleship on which the Japanese surrender was signed, is moored on Pearl Harbor's Ford Island. But in 1941, this is where the USS Oklahoma was attacked. After being hit by several torpedoes, she capsized. The Oklahoma's elaborate salvage plan involved the installation of 21 large winches on Ford Island, an equal number of towers attached to the ship itself, and steel cables rigged between ship and shore.
Essential to the riding of the Oklahoma were electric motors. And what they came up with was a recycled motor that was once used on the Honolulu trolleys. They devised a way that they could pull the ship over slowly over a period of days, months, almost a year. Without that motor, that slow process could never be done.
The ship came afloat in early November 1943 and was sent to dry dock for final repairs. After this Herculean effort, the Oklahoma was deemed too old and damaged to return to service. There were never plans to raise the Arizona, and she remains beneath the memorial to those who perished during the attack.
In the assessment of this battleship, they found that she was unserviceable. Her damage was so extensive, but she was salvageable, and they would take the upper works or her superstructure, cut it away, and place it in a scrapyard so they could be used in the war effort. But the two aft turrets, turrets number 3 and 4, those were taken from the ship and placed as coastal guns here in Hawaii, so they did serve another purpose. But the other part of it was that the crew, nearly 900 men, still rest inside that ship.
The Pearl Harbor salvage operations helped alter the course of history. But one recent spectacular salvage project was not about changing history. It was about preserving it. The effort to salvage the damaged ship stationed at Pearl Harbor in 1941 required Navy and civilian divers to spend 20,000 hours underwater. Deep Sea Salvage will return on Modern Marvels. Salvage divers spend a great deal of time beneath the surface. They have to rely on their equipment and each other. Surface supplied diving is a team effort, especially when dealing with a diver's umbilical, their lifeline while working below.
Each umbilical is made of 3 elements. The yellow element is your air element, sends air down the diver so they can breathe. The blue is your pneumofathometer, and it tells topside how deep the diver is based on the water pressure, sends air down to the bottom, and based on how much pressure is down there, topside can tell how deep the diver is. The red is a strength member in your communications cable. It allows topside to talk to the divers, and it also supports the weight of the diver.
Another piece of dive equipment always close by during deep dive operations is a recompression chamber. It's designed to remedy decompression issues, including the condition commonly called the bends.
Okay, in the chamber.
If a diver comes up too fast, the gases that have been pressurized in his body can create bubbles in his bloodstream. A simple comparison is opening a carbonated soft drink.
In the chamber, get around the vitals.
The bubbles appear in the liquid when the pressure is released. A light case of the bends may cause joint pain. Worst cases involve bubbles that lodge in the spinal cord or brain and can cause paralysis or death. In a recompression chamber, a diver is repressurized so the bubbles dissolve back into the diver's blood, and then he is slowly brought back to normal surface pressure. Emergency decompression issues are kept to a minimum for Navy divers by the careful adherence to the guidelines in the established dive tables. These rules dictate how deep they can go, for how long, and what gas they should be breathing. It's the Navy Experimental Diving Unit, or NEDU, located in Florida, that keeps divers safe. It's the Center for Military Diving Research and Equipment Testing and Evaluation.
Anytime the Navy is interested in a piece of equipment or want to modify something they already have, we first get that equipment down here in the unmanned testing department. One of the things we have is a mannequin head, which we can instrument. We can put sensors in to measure various things, and then we would take the hyperbaric chamber to various depths by compressing it with air.
We have breathing machines there that can simulate lungs that no human on Earth has. And we breathe them at every temperature and at every breathing rate with every kind of gas that we ever expect to put in them. Before we put it on a guy, we want to make sure that structurally, design-wise, and every other way, shape, and form we can tell, this is a solid piece of equipment that's been designed well and is designed to function.
The NEDU not only devotes a great deal of attention to equipment, but also focuses on the biomedical effects of deep-sea dives on the human body. It tests and observes these effects in its ocean simulation facility.
The structure is designed to have a 5-chamber habitat on the upper level, connected by a trunk, and at the bottom of the trunk is a 55,000-gallon, 47-foot-long wet pot. The entire structure is made out of HY80 steel.
In the ocean simulation facility, temperature control ranges from 28 degrees Fahrenheit all the way up to 105 degrees.
Stand up and unhat.
After air or gas is pumped into the sealed chamber, the atmosphere in the habitats on the upper level and in the wet pot below can be pressurized to replicate depths up to 2,250 feet.
All divers, when you're ready to travel, give me OKs in front of your horn. "50 feet, 60 feet.
The NEDU was instrumental in the development of mixed gas diving and continues to analyze the benefits of different gas ratios.
We have a storage capacity of over 1 million standard cubic foot of gas. We use air, helium, and oxygen and nitrogen. We have the capabilities of mixing all of those gases together to obtain whatever mixture we need for a particular dive, usually driven by whatever depth we're doing or the particular type of equipment that we're using.
To properly test the equipment and gas combinations, the divers ride bikes while in the water.
The bikes, we put 50 to 60 watts of resistance on it. It makes the divers breathe harder while they're on the bottom, and it simulates work that would be done on the bottom on a real job.
As a result of the research done by the NEDU, Navy regulations require that its divers working below 190 feet breathe mixed gas. The normal air we breathe is primarily made up of nitrogen and oxygen. But when the human body is under the pressure of a deep dive, it processes these gases differently. Nitrogen can cause a disorienting feeling like drunkenness, and oxygen's adverse effects include nausea and convulsions. For deep dives, a combination of helium and less oxygen than in normal air has proven most beneficial. Navy divers were able to utilize the advantages of mixed gas diving during the mission to recover artifacts from the hallowed Civil War vessel, the Union's USS Monitor. It was 9 months after its famous battle with the Merrimack in March 1862 that the Monitor, with its innovative rotating gun turret, sank off the coast of North Carolina. In 1998, working with the National Oceanic and Atmospheric Administration, Navy divers, breathing a mixture of helium and oxygen, began artifact recovery from the Monitor's resting place, 240 feet below the surface.
Just diving on the Monitor, especially for a naval officer, is a pretty emotional dive. You see this Civil War ironclad ship that really changed the course of naval history, and you're walking the decks of your naval ancestors.
Because the Monitor project was of such archaeological importance, all Navy divers wore helmet-mounted cameras, so those above could see what was happening.
The helmet cameras on the Navy's dive suit was incredibly beneficial to the archaeological team because we weren't allowed to dive with the Navy, so there had to be an incredible amount of trust factor to what was going on.
If we got to the point where we were removing something or cutting something, where to cut and how to cut it, and it really got to that degree where each diver was really working with the archaeologist and actually working as the hands for the archaeologist.
In the summer of 2002, the Navy divers were ready to help raise the Monitor's gun turret. First, they had to remove a section of the Monitor's hull and armor belt that had covered the gun turret since the ship capsized in 1862. Next, divers removed the added weight of sand and debris from inside the turret. Then they attached a custom-built lifting mechanism so that the entire 9-foot-tall, 120-ton turret could be raised to the surface.
This is the actual spider mechanism that was designed and built specifically for this operation. Now, when the spider was lowered down, each of these legs would be extended out 15 degrees so that when we lowered the spider onto the turret, we didn't have a danger of banging up the turret or damaging it. And then utilizing hand-operated hydraulics by the diver that would bring the legs back into the position like this that you see here so that the feet were underneath the lower lip of the turret to bring her up.
On August 5th, workers using a 500-ton capacity crane lifted the turret out of the water and secured it to the deck of a barge for transport to the Mariners Museum in Newport News, Virginia. Some of the contents recovered from inside the turret included 2 11-inch Dahlgren cannons, along with some skeletal remains and artifacts from a few of the men that went down with the ship nearly 150 years ago. The Monitor project lasted 5 years, allowing plenty of time to plan and build specialized equipment. But many salvage missions are crises that need to be dealt with immediately. 2 even posed the threat of nuclear disaster. Navy divers made their first operational use of a helium-oxygen breathing gas mixture in 1939 as they salvaged the submarine USS Squalus. Deep Sea Salvage will return on Modern Marvels. One of the major challenges of deep sea salvage has always been locating an object on the ocean floor. Wind and currents may have carried clues like floating debris for miles. An underwater search often begins with the deployment of a side-scan sonar. Referred to as a towfish, it is designed to glide above the ocean floor so it can scan the bottom while pulled by a cable attached to the ship above.
What you're seeing here is the topside console, or the operator's console, for the side-scan sonar system, and this represents state-of-the-art. And what you see here is information as it would be seen from the towfish. You see that the center would be the towfish, out to each side represents 150 meters. We spend 12 hours a day, every day, for up to, well, as long as it takes, a month, 2 months, to look for one red blob on a screen.
This particular blob is a sunken helicopter, but side-scan sonars can capture images of metal objects as small as a quarter. Once the object is found, ROVs and submersibles now make it possible to conduct salvage operations thousands of feet below the surface. But during a crisis involving a lost nuclear submarine in the early 1960s, the Navy had only one way to go deep: the Trieste. Now on display in Washington, D.C.'s National Museum of the U.S. Navy, the bathyscaphe Trieste, designed by a Swiss scientist, was purchased by the U.S. Navy in 1958. The upper portion is made of fuel and water ballast tanks, while the operators are housed in the small bell on the bottom of the craft. The Trieste was used in a series of historic deep submergence tests in the Pacific Ocean, including a dive in the Marianas Trench, the deepest spot on the ocean floor, to the record depth of 35,798 feet. After just 20 minutes at that depth, the operators began their ascent by releasing the weight of the iron pellets held in 2 hopper-like silos. In April 1963, a missing atomic submarine, the USS Thresher, sank in about 8,000 feet of water. At that point, there were no other submersibles that could dive that deep, other than the Trieste. The enormous bathyscaphe was transported to the east coast of the United States to aid in the critical search taking place about 200 miles off the coast of Massachusetts. The Thresher had imploded on its way to the bottom, so the immediate concern was that the nuclear reactor in the submarine's engine room might have ruptured.
based off of photographs that Trieste was able to take of nuclear submarine Thresher and the few pieces of the submarine that Trieste was able to recover and bring to the surface, the Navy determined that there was a massive pipe failure on board the submarine, and that's what caused Thresher to sink.
Radiation detection equipment confirmed that the nuclear material in the submarine's reactor was still contained. The Navy decided to leave the submarine on the bottom. Subsequent tests over the years have shown no radiation leakage. Trieste was decommissioned shortly after its successful search for the Thresher. It was replaced by the new Alvin submersible. The Alvin was not designed to operate in the same extreme depths as the Trieste, but was much more maneuverable and better equipped for search and salvage operations. Luckily for the Navy, it had completed its initial tests just in time to aid in a potentially even more disastrous nuclear crisis. This time, it was a missing H-bomb.
On January 17th, 1966, a B-52 bomber flying over the coast of Spain collided with its KC-135 tanker. During that collision, 4 hydrogen bombs were released and dropped to the coastline of Spain. 3 of those bombs were found almost immediately.
The bombs were not armed, so there was no chance of a nuclear detonation. Nevertheless, loose nukes posed just as frightening a problem in 1966 as they do today. After combing the countryside, search teams found no trace of bomb number 4.
There was an important clue to the location of that bomb. A fisherman had seen a parachute pass over his boat, dangling what he thought was a man, a dead man, and then descend into the water near his boat.
The Navy began a major underwater search. Divers combed the shallow waters, and the Alvin and other submersibles scanned the ocean floor below diver depths.
Very soon after that, Alvin noticed a track where it was searching that looked like a torpedo had been dragged over the bottom.
After weeks of surveying and photographing the ocean floor, the Alvin's crew located the bomb, sitting on a steep slope, 2,550 feet below the surface.
After the H-bomb was found on the 15th of March, an attempt was made to recover it. Alvin went down with a line and attempted to attach this line, wrap it into the shrouds of the parachute. Unfortunately, when the lift attempt was made, the line parted and the bomb once again dropped into the depths.
This time, the Navy decided to use an unmanned device originally designed for torpedo recovery, called the Cable-Controlled Underwater Recovery Vehicle, or CURV. It would attempt to attach grapnels to the chute.
Unfortunately, CURV itself got tangled in the parachute, and a decision had to be made to lift it. That moment was so tense that on board the recovery ship, one of the individuals that was in charge of CURV fainted dead away. But the lift was made, CURV was brought near the surface, divers were sent down to secure much heavier lines on it, and then it was finally recovered.
Bomb number 4 was out of the ocean. The 81-day saga of the missing H-bomb was finally over. Navy divers have proved adept not only at averting nuclear disasters, but also environmental catastrophes. Recently, one that was nearly 60 years in the making. The Alvin submersible was built by General Mills Electronics Group in the same factory used to manufacture breakfast cereal producing machinery. Deep Sea Salvage will return on Modern Marvels. Two highly trained Navy dive teams are dedicated to rescue and salvage operations. Mobile Diving and Salvage Units 1 and 2. Mutsu 2 operates out of the Little Creek Naval Amphibious Base near Norfolk, Virginia, close to the safeguard ships Grasp and Grapple. Mutsu 1 is stationed in Pearl Harbor, near the Salvage. When not out on a job, team members can be found testing their equipment and themselves. Mudsuit teams must keep themselves in a state of constant readiness and prepared for any contingency. In deep sea salvage, the one thing that can be counted on is that no two jobs are alike. Recently, for those stationed in Pearl Harbor, a sunken ship from World War II suddenly demanded attention. The oil tanker USS Mississinawa went down with over 2 million gallons of oil on board, and it was starting to leak. In 1944, the oil tanker was anchored northwest of Guam in the Ulithi Lagoon. On the morning of November 20th, it was struck by a Japanese manned suicide torpedo. The 553-foot-long tanker containing aviation fuel and oil burst into flames. The Mississinawa slowly sank and took 50 of its crew to their watery grave. For the next 57 years, the Mississinawa, with most of its cargo still held in several undamaged internal tanks, lay quietly on the bottom. It is believed that the corroding wreck first began leaking oil in 2001, during the rough seas caused by a typhoon that passed through the area. The discovery of the oil leak caused concern of an impending environmental disaster.
The whole community of Ulithi Atoll is a seafaring, very tribal, very small group. And what we were worried about is oil from that wreck leaking out and then destroying an entire people's way of life.
Raising the Mississinawa was out of the question for two reasons. Trying to move the unstable wreck could cause a major release of oil. Plus, the ship was a designated war grave for those entombed inside. The Navy decided that the oil had to be removed from the wreck as it lay on the bottom of the lagoon. The Salvage moored over the wreck, which lay upside down 130 feet below. The main technique that divers used was installing 20 valve assemblies called hot taps to remove the oil.
So what we did was attach the hot tap on the external hull and then finish drilling through the internal tank boundaries until you had oil.
After the divers installed each hot tap, they removed the upper part of the device and attached a hose. The oil was then pumped up through the hose at the rate of 450 gallons per minute to a barge moored next to the Salvage. Divers also cut holes in the hull to access 2 internal oil tanks and removed remaining oil from the engine room and pipes.
We removed a total of 2.1 million gallons of oil, which, you know, a significant amount of oil, and she was starting to deteriorate, and that's why they were starting to see oil leak from her, and it just would have gotten worse. And so, yeah, we eventually averted a pretty significant spill.
What little oil remained in the Mississinawa no longer posed a threat to the environment or to the people of Ulithi. The crew of the Salvage and the Mudsuit divers had helped avert an environmental catastrophe. They returned home to Pearl Harbor, knowing that at any moment, enemy combatants, mechanical failure, or the unpredictable sea could create yet another candidate for their never-ending